Okay, let's finish up 1-1b. Okay, in case Julie and Naomi are listening to this, we hope you guys did well on your tennis match today. All right, so we're going to finish up. We're going to focus on the graphing part of limits today. And we've talked a little bit. I drew a graph just now, but we're really going to focus hard on the idea of how we can use graphs. And we're going to talk about the difference between a one-sided limit and a two-sided limit. Okay? All right, so in calculus, we talk about numbers having two sides. You've already seen that with 0. 0 is a two-sided number. One side of 0 is positive. What's the other side of 0? Negative. That's the only number whose two sides are different in nature. They have different signs. The right side of 0 is positive. The left side of 0 is 1. So the answer to that question, what's the only number whose two sides have opposite sides, is 0. We have 0 plus versus 0 minus. Okay, so having two sides. It's the Dr. Jekyll and it's the Mr. Hyde. It's either positive or it's negative, just depending on what side of 0. Okay, so we're not going to just be talking about 0. I'm going to specify, well, which side of 0 are you talking about? Because it's going to matter. Now, it really starts to matter when we talk about functions like squares. All right, so what happens when you plug in a two-sided number into a square? So let's look at that. Let's start with 2 plus. That's the greater side of 2. So if I plug 2 plus and I square it, so it's something that's already bigger than 2. And if it's already bigger than 2 and I square it, what am I going to get? Something that's bigger than 4. Now that's sort of a logical one. It started out bigger than 2. If I multiply it by itself, it's going to be bigger than 4. What if I start out with something that's smaller than 2?
It's still something greater than 4.
Okay, something smaller than 2, like what? Give me a number small on the left side of 2, something smaller than 2. 1.99999. If I square 1.9999, where do I end up with on 4? Which side of 4 do I end up on? Well, I started out with something smaller than 4. When I square it, I can't be bigger than, something smaller than 2. When I square it, I can't magically be bigger than 4. I have to be smaller than 4. So that's going to turn out to be 4 minus. Okay, what about 0 plus? If I square that. So I'm starting out on which side of 0? The positive side. If I start out on the positive side of 0 and I square it, where do I end up? I'm still on the positive side of 0. Because if you square something that's positive, it's still positive. What if I start out on the negative side of 0? Okay, if I start out on the negative side of 0, so something that's negative, I square it, which means I'm multiplying a negative by another negative. What do I end up with? Positive. So this is the first time now we jump to the other side. Okay, all the other ones we've seen so far, I started on the right side of 2 and I ended up on the right side of 4. I started on the right side of 0, I ended up on the right side of 0. I started on the left side of 2, it stayed left side. So right to right, right to right, left to left, it all matched. But here's the first one where you start at the left side of 0 and you end up on the right side of 0 because you squared it. Okay, now let's talk about negatives. All right. I'm working with the number -3. If I'm just talking about straight old plain -3 and I square -3, what do I end up with? 9. Okay. Now let's talk about sides. If I'm starting on the right side of -3 and I square it, which side of 9 do I end up on? End up on the left side of 9. Started out on the right side of 3, but the left side of 9. Now for me, when I'm talking about negatives, I like to think of it on a number line. Or I like to think of it actually with specific numbers, okay? I'll say, all right, not -3 plus. Let me give an example of a number that is actually -3 plus, and something that is on the right side of -3 is -2.999. That's a number that is on the right side of 3. And when I square that, it's going to be +9, but because those decimal values are not quite to an absolute value of 3, then you end up on the left side of 9. The reverse happens when you do negative 3 minus. Okay, so again, I think, well, what is negative 3 minus? An actual value that would be to the left side of negative 3 is negative 3.001. It's farther down the number line to the left. And if I square that, I still end up on 9, but on which side of 9? And I end up on the plus side of 9 that time.
When we're talking about to the left side, is it just 2, 0? So, for example, if it's like 3 to the left, does it just go 2, 0? Or if you keep going past?
3 to the left or negative 3 to the left?
Positive 3. If you go positive 3 to the left, does it just stop at 0? Or?
No, like positive 3 to the left is microscopically small. Positive 3 to the left is like 2.9999999. Okay, so we are not talking about a big distance here. It's an infinitesimally small difference. Yeah, microscopically small. All right, so understanding the two-sided values of numbers can help us understand what are called one-sided limits. And so you'll be looking at limits on one side of a number versus the other. And those can be different values depending on which side of the number you're on. Just like we saw here, you end up with different values depending on which side of the number that you're starting on. Okay, so a one-sided limit, we talk about approaching from the right-hand side or approaching from the left-hand side. Sometimes those values are the same, but sometimes those values are different. And so that's what is defined as a one-sided limit. So you'll notice when it has the little plus or minus on the value that the x is approaching, okay? All right, we talk about these algebraically, but a lot graphically. Okay, so here is a drawing graphically where there's a hole in the graph, but the graph has limits both on the right and the left-hand side of 1. Okay, all right, so let's start kind of comparing the limit as x approaches 1 of f of x, the limit as x approaches 1 minus the left of f of x, and the limit as x approaches 1 plus of f of x. Okay, at 1, at exactly 1, what's happening at the graph? There's a hole. Okay, at 1 exactly, so if I look, okay, right up here, okay, there is a hole. And so we say that does not exist. Okay, there is no value right there. But now if I look at 1 to the left or 1 to the right, okay, so 1 to the left would be, let me switch colors here. Okay, 1 to the left would be just like this. Okay, what integer value is it close to?
2.
It's close to 2, but which side of 2 is it on? Is it less than 2 or is it bigger than 2? Higher than 2 or lower than 2?
Lower than 2.
Barely lower than 2. So we say the answer to this is a little bit less than 2. Just a tiny bit, microscopically less than 2. And then 1 plus, okay, if I'm on the right side, okay, the integer value it's closest to is 2 again, but this time I'm higher than 2, so I'm at 2 plus. So you've got a 2 minus and a 2 plus. Any questions on that? All right, how about this one? Find the limit approaching 0 of 5 over x. All right, well, what's happening at 0? Okay, there's an asymptote right at 0, okay? So since there's an asymptote, then I have to investigate this differently. I need to look at, well, what is happening on the left side of 0 of the function 5 over x, and what's happening on the right side of 0 of the function 5 over x. The name of this function is a hyperbola. It's got its branches. Okay, so let's look at just the left side of 0, barely to the left. So if I look at just barely to the left of 0, and I try and come down and connect with the graph, okay, how far down am I going to go?
Infinity.
I'm going to go to negative infinity. Okay, so the answer to 0 minus is negative infinity. And on the other side of the graph, on 0 plus, okay, and I tried to connect with this graph by going up, okay, how far up would I go? That time I'd go to positive infinity. So you do have to always specify the negative sign if you mean negative infinity. For positive infinity, you don't have to put the plus. If you just write infinity like that, the default is you mean positive. Okay, you don't have to specify one or the other, but you do have to for negative. Okay, any questions on that one? Yeah.
So is the limit, the actual limit for just x equals x going towards 0 without this?
Correct. Okay, so this is what's called a piecewise graph. Not very exciting in its name. It's called piecewise because it's made of different pieces. Each piece has a different kind of slope and a different position, so that's why they call it piecewise. Okay, you can find different one-sided limits at the different critical points. So the critical point, the first critical point is the end point, -4. What side of -4 is the only side that exists in this graph? Okay, -4 on the right. There's nothing on the left of -4. This graph stops. And so the only thing that exists is -4 plus. And then you put f of x, okay? You always have to have something. I'm referring to the given graph. Actually, I don't know. It doesn't tell me it's called f. It could have been g or something else, but we'll call it f. Okay, and so on the right side of -4, again, we just kind of look at it, and I'm on the right side. I trace that down, and the closest integer that I'm going to be coming to, the closest integer is -3. But what side of -3 will I be on? A little bit more than -3 or a little bit less than -3? A little bit more than -3, okay? The next critical point, what would you say? Yeah.
Why isn't it like just -3 since it's like a closed dot?
A closed dot. Now, if I had said -4 on the button without the plus, then it would be -3. Okay, what's my next critical point, do you think? -1. Yeah, that corner, that vertex. And how many sides exist there? Yeah, I can do both. I can do -1 on the left. I can also do -1 on the right of f of x. Okay, and so -1 on the left, it's closest to the integer value of 2. But which side of 2 is it on? Okay, it's lower. We're talking about the y value, so it's lower than 2. Okay, what about on the right? Okay, the integer value it's closest to is 2. Okay, on the right side now, is that higher or lower than 2?
It just is 2.
It is 2. It's just right on, because why?
Because it's a straight line.
They're all straight lines.
Because
It's a horizontal line, okay? They're all straight lines. All right, the next one I could do, the next critical point would be 3. And I could look at, all right, are my limits on the left side of 3 compared to the limit on the right side of 3? And on the left side of 3, the closest integer value is still 2. And it's right on 2, because again, that's a horizontal line. But on the right side of 3, the closest integer value is -2. And again, it's just -2 because it's part of a horizontal line. And the last critical point would be the end point of 4, but it only exists on the left side. There is nothing on the right side of, +4, and that's still the value of -2, again, because it's part of a horizontal line. All right, any questions on that one? Yeah, Chloe.
Why for like the left side of 3 is it not like 2, like to the left?
For the same reason that this one isn't higher or lower than 2. Both of these are on a horizontal piece, and so it won't ever be higher or lower than 2 because it's completely flat with a 0 slope, so it'll always be exactly 2. Okay, the slope is, if it had a different slope than other than 0, then those values would be changing, but we call that a constant slope. Okay, so then you've got two-sided limits. A two-sided limit is where the one-sided limits match. Okay, a two-sided limit is where the left and the right side limits match. Did we have any of those here? Okay, did we have any limits? Let me erase here. Oh shoot, once I've left the page, I can't. Okay, did we have any where the left and the right side were matching? And a match is literally just the same integer value.
So
Okay, the same integer value. So I'm going to argue that, yes, this. Okay, the same integer value. It does not matter that there's a little minus by one of them. They have the same essential integer value, and they are the left and the right matching each other. That would be called a two-sided limit because each side matches and has the same value. Okay, so the formal definition of that. Okay, do you see how they use the mathematical notation here? Okay, that means it goes both ways. Means the converse of the statement is also true. Okay, if one, then the other, and then you can flip-flop it, and then if it's also true the other way. Okay, so the limit at C in general is going to be equal if and only if C plus and C minus are both equal to the same L integer value. So L is an integer value, and if those two things are the same, then the overall limit exists also at L. So that can be proven both ways. Okay, you can say, all right, well, if I'm told that the limit equals L, then the implication is that the left and the right have to both equal L. Or if I'm told that the left and right both equal L, the same integer value, then I can assume that the other limit also equals L. It goes both directions. All right, so here's how you would approach this from an algebraic standpoint. Okay, I can do several different one-sided limits here. So let's count up how many we could do. All right, I can do a one-sided limit here, but on which side of -2? Only on the right. It's only for things greater than -2. So I could do an investigation at -2 on the right. It's only things that are bigger than -2. I could also investigate the number 1. And so I'll be looking at 1, but on which side of 1 am I on according to that inequality? I'm on the negative side. All right, for both of those, I will be using x plus 2 as my rule, because both of those are in the piecewise part of x plus 2. So algebraically, I'm going to drop the number into that and add 2. So if I take -2 plus, drop it into x plus 2, so I'm adding 2 to it, what integer value do I end up with? But on which side of 0 am I going to be? If I started on the right side of -2, I'll end up on the right side of 0. Picture it. Okay, if you put yourself on a number line and you start out on the right side of -2 and you add 2 whole units, that'll bump you up 1 here, and then it'll bump you up 1 right there, and now you're on the right side of 0. If I put 1 in, what integer value will I end up with? Okay, I put the number 1 in here. What integer value will I end up with? 3. But which side of 3 will I end up with? Why? So I'm plugging in something I'm plugging in 1 exactly? No, I'm plugging in something that's a tiny bit smaller than 1. So I'm not going to get 3 exactly. I'm going to get something a tiny bit smaller than 3. Okay, let me give myself a little space. All right. So then I'm going to investigate the next 2. So that'll be this end and that end. So I'll do, all right, 1 from the right, and I'll do 3, but the inequality says 3 from the left. And this time, the equation, the formula I'm using is -1, which is a constant number. What's the slope of -1? 0. It's a horizontal piece. Therefore, the result of this will be an integer without sides to it because it's a horizontal line. So will this one. Okay, and then the last one, I can look at 3, but I can only look at the right of 3. That's using this one here. So now I'm using the formula negative x plus 2. Okay, so if I drop 3 into that, and I put 3 here and make it a negative, and then add 2, what integer value will I end up at? -1, right? But which side of -1? If I'm plugging in -3 plus, add 2, I should end up with -1 plus. Okay, now, which of these, those are all my one-sided limits. Which of them qualify as two-sided limits? So to check, you check these two. Okay, why do I check those two? Because it's both sides of 1. And now I compare their values. So I have the integer value of 3 and the integer value of 1. Does a two-sided limit exist there? No. The two-sided limit does not exist. The other one I can check is this one because it's one side of 3 and the other side of 3. And I compare their integer values, and are their integer values the same?
Yes.
Yes. And so this is the only one that qualifies as a two-sided limit. Okay, the other one doesn't. It does not qualify because 3 and -1 are not equal. But -1 and -1, just their integer values are the same. And so that's the only two-sided limit you have. So on a visual, a two-sided limit looks like a full corner where both edges of the corner meet. Okay, this one here is not a two-sided limit because there's a big gap. Okay, a two-sided limit has to connect on a graph. A two-sided limit algebraically, you have to show that the integer values are the same.
So even though like not in the same row, they still can go together.
Mhm. Mhm.
Okay.
Yep. All right, so several two-sided limits here. There's a two-sided limit here because of the connection point. There's another two-sided limit here because of the connection point. The ends are not two-sided limits because you only see one side of it. Okay, we only see -3 minus, so that is not a two-sided limit. And we only see +3 plus, that is not a two-sided limit. Okay, I'm gonna have you practice this for 5 minutes. There's a little worksheet in your Canvas, and with the person who's sitting directly next to you. So I'll put more of you guys can go together. I guess you're each missing, but okay, just everybody pair up. I think this will all work. I'll put you with no. Sydney, go work with Caitlin, okay?
Okay.
All right, so just pull it up in Canvas, and it's just a quick, like, little video, worksheet, but it's a picture to look at, and you and your partner. So you guys are together. That's it. All right. So
What is it?
I'm sorry. You can work with Jonathan. I'll have you work with SK.
Okay.
Okay. All right. So you can go move.
With SK? Or no?
Yeah. Or you can come up here. Is that easier? All right. Did you find it in Canvas?